This is part 2 of lecture 5 of the neurodynamics series. Today we will talk about stability in 2D systems. Actually, not only 2D, but also higher dimensional systems, but we will restrict to examples in 2D. For that, we would first like to review stability in a one-dimensional system. When we characterized one-dimensional systems, we realized that the change of the system is described by a differential equation, as you can see on the right-hand side, and the system is not subject to any change if the differential equation equates to 0. That means that v dot is 0 and f of v is 0. This is a necessary condition for an equilibrium that can be either an unstable or a stable attractor. If we plot this in a one-dimensional system, we are following the curve f of v that describes the change of the system. In this case, that is this line, and we are computing the points at which this curve is crossing 0, which are these points which we call equilibrium. Based on the change in the very near vicinity of the system, we can characterize whether that is an attractive or repelling system. If it's attractive, then from both sides the system will approach the fixed point. That means any small perturbation, for example due to noise, would push the system to the right or to the left side, and as a consequence of that it would feel a force pushing it back to the origin. That means the system will always return to the fixed point. For the unstable fixed point, that is different. While it's right on the fixed point, the system would not feel any force, but any small perturbation would bring it away from this point, and then it would be pushed further away from this fixed point, and that's why we call that unstable fixed point. Associated with each fixed point is therefore the so-called attraction domain. That is the domain that is associated with that, and everything inside this domain, every condition inside this domain, would finally lead to a state that ends up in the stable attractor. We characterize stability in a one-dimensional system therefore based on the derivative, and we realize that if the derivative is negative, like in this case, we have a force that is actually pushing rightwards on the left-hand side and leftwards on the right-hand side, and therefore we have a negative slope. So what we do is we're computing the candidates for fixed points. That is equivalent to looking for the zero crossings of f of v, and all zero crossings we compute the derivative of f of v at this very same point, and that means we compute the slope, the first derivative, and we are looking whether the slope is negative. If the slope is negative, we identify that as a stable fixed point, and if it's positive, then we identify this as an unstable fixed point, corresponding to the figure on the right hand side. So in that sense, determining a stable or unstable fixed point in a one-dimensional system is easy. We identified a few necessary conditions based on that. Because we know that f of v usually is smooth, we can directly infer from that in a one-dimensional system, two stable equilibrium points have to have an unstable equilibrium point in between, just simply based on the fact that once you had a positive slope and another positive slope, it needs to be intersected with negative slope. Or if you have two negative slopes and zero crossings, then in between have to be a positive slope at a zero crossing. If we talk about a two-dimensional system, then we have to extend the concept of an attractor. An attractor for a one-dimensional system was essentially a point that the system was approaching to or repel from. If we have a two-dimensional system, we can actually extend this concept of an attractor based on other stable solutions, because an attractor is essentially a stability of a certain behavior of the system. Stability, of course, is guaranteed if you stay at the very same point, but stability of behavior could be also guaranteed. For example, if you have a so-called limit cycle, that means that the system will repeat the very same circular pattern in a two-dimensional system. We also call that attractor. It's not a point anymore, but it's a circle. It's a circle that is attracting all nearby points such that the system is ending up on a periodic pattern that is repeating the very same activity over and over again. So that means we need to extend for more than one-dimensional systems the concept of an attractor to other types than simple fixed points. And in the next slides, we will talk about that and associate a concept of stability and how we can actually determine this concept of stability in more dimensional systems. So if we extend the concept of an attractor to an n-dimensional system, we also have to define stability. For a one-dimensional system, we defined a rigorous definition of stability, that is, the system is stable first if we have the necessary condition fulfilled that is not changing. That means f of v equals 0. And then we looked at the slope to define whether it's stable or unstable in terms of the attraction domains and the behavior close to the fixed point. We would like to extend this concept of stability to more than one-dimensional systems, to the higher dimensional systems. And we can do this. We, for example, identified that if we have a two-dimensional system or high-dimensional system, that we can also have closed orbits like a circle. If we have such a closed orbit, then the system is repeating its very same activity forever if it's stable. Mathematically, we can define this extended version of stability simply by saying an equilibrium is stable if any trajectory starting sufficiently close to the equilibrium remains near to it for all times. And if in addition all such trajectories converge to the equilibrium, if we wait infinitely long, then we say that the equilibrium is asymptotically stable, which means the systems, the different points that we can initiate the system in, will approach the equilibrium finally if we wait long enough. For a two-dimensional system, that could, for example, mean, like here on the left-hand side, that we have trajectories that actually end up in a single point. Then we have stability, because wherever we start in this phase diagram, we will always end at the very same point in the center. And if we also look at the speed, we would have to show that actually in an infinite amount of time the system would be exactly on the center of the system, and then we would say it's asymptotically stable. If we compare that to the right hand side, you see that there is an unstable fixed point. The difference is that in both directions we have repelling forces that actually bring us away from the center. So that means wherever we start, we never reach into the center, and therefore it's unstable. So if we classify then equilibriums that call unstable and stable, it's easy, because everything that is not stable we call unstable. There are only two classes. The necessary condition for a stable equilibrium is that actually from all points nearby the trajectory it has to reach the fixed point or the limit cycle. In that case, that means that actually both directions for a two-dimensional system needs to be attractive. It's sufficient if one of the two directions would be repelling. We would render the system unstable. If both, like on the right hand side, are repelling, it's of course also unstable. For a limit cycle, that would mean that if we have a limit cycle that would be stable, this limit cycle would attract all trajectories from the outside, that finally the activity would end up on that limit cycle. And the same would happen from the inside. If we start somewhere in the inside, the system would essentially approach the limit cycle, and once it's on the limit cycle, it would repeat the very same activity in a periodic fashion forever, like this. So the limit cycle would be stable because from wherever we approach it, it would end up on that limit cycle. We will not actually focus on the mathematical analysis of limit cycles at the moment. And this is just for the reason that we want to keep it simple. So the next analysis that I will introduce is a stability analysis in 2D that actually characterizes the properties of fixed points in 2D. And a fixed point is an equilibrium that is a point. And this fixed point can be either stable and unstable. On the last slide, we saw two examples. So that means if we define a formal stability analysis, we first look at the two functions that define the change in respect to x and y. If we have two differential equations, then the change of the first differential equation is defined by f, and the change of the second differential equation is defined by g. If it's a fixed point, then of course we know that one sufficient or the sufficient condition for determining that the fixed point is existing is that there is no change in any of the two directions. That means f and g both have to be 0. So step number one in identifying fixed point in a two-dimensional system is looking for solutions for which f and g of the given system are 0. Geometrically, we can interpret this as the intersection of null clines, because each of the null cline defines one of the two functions to be 0. And at the intersection of the two null clines, both functions f and g are 0. So strictly speaking, we now know if we put a system on exactly the solutions at the point where both f and g are 0, the system will stay there because it doesn't feel any force. That means this qualifies for the concept of an equilibrium. However, if we would apply any small noise again, the system would bring us away from this solution, and the system would immediately feel a force. That means we then have to distinguish between a stable and unstable equilibrium, because only for a stable equilibrium the system would push the point back into the center in both directions, while for an unstable fixed point the system would be pushed away, repelled in at least one of the two dimensions. If the system is pushed back into the equilibrium point, and this happens in sufficiently fast, we say that it's asymptotically stable. So this explanation already highlighted that we need to understand what is happening in the very close vicinity of the fixed point to understand whether it's stable or unstable. So looking at this graph, we start first by looking at the two null clines, which we have here, and the intersection of the two null clines give us the fixed point condition. To understand whether it's a stable fixed point as on the left hand side and an unstable fixed point as on the right hand side, we need to understand whether the forces actually push us back into the center if the system was subject to a very small perturbation. If we do this, we realize that the principal behavior in each of the quadrants is actually identical. In each of the quadrants, we have forces that actually push us back to the center wherever we start, right? So that means we realize immediately that instead of characterizing the entire phase space surrounding the system, it's sufficient to only look at the very close vicinity, because the principal behavior in terms of the attractive or repulsive behavior is identical to the overall behavior in the entire other 4 quadrants. The reason for that is that the null clients intersect the entire phase space in the 4 different parts. So that means instead of looking at the different quadrants at all places, it's sufficient to look only at the very near vicinity at the point. We call this, therefore, local linear analysis. That means we're looking only locally at the very near vicinity of the point. The reason that we call this linear analysis will be apparent in a second. To formalize our problem now mathematically, we say that we explore just the close proximity at the proximity of the equilibrium that we identified. The equilibrium that we identified is the necessary condition that the change rate x dot and y dot at this very same point is 0. And we characterize then the function f and g that are determining the orientation of the vector field in this very close proximity, and characterize their behavior subsequently. Again, to keep it simple, we're looking at the most simple case at the moment, and that is we assume that we have an equilibrium at the origin at 0, 0. That means for x equals 0 and y equals 0, the change rate x dot and y dot is 0. If we do this, we now need to characterize f and g close to the origin. So if we plot this, and we have 0, 0 here, we need to understand whether we have a vector field close to the origin that is pushing us back to the origin if the system is subject to noise, or whether the system, for example, would be repelled because in one of the 2 dimensions the system would be attractive and in the other one it would be repelling. If we do this, we would have to analyze this complicated function f and the complicated function g that can have like an arbitrary complex shape. From Taylor analysis, however, we know that if we have such a function, we can approximate that. And in neuroinformatics, we used polynomials, for example, to model complex functions with their very same kind of motivation. So instead of looking at the arbitrary function f and g, we are transforming the function and developing it in terms of a polynomial expression. So if we have a certain dependence, let's say this looks like this in the surrounding, then we try to approximate that function with a polynomial order that could be the constant plus alpha times x plus beta times x squared and so on. And we could determine the different parameters, alpha, beta, gamma, and so on, that are necessary to approximate this function. So we know this works in principle if we have sufficiently many of the polynomial orders, right? However, that wouldn't help us, because that would essentially mean we replaced one complex function f with another complex function which is now expressed in terms of a complex polynomial. But do we really need all these polynomial orders? Well, if we have a function that is characterized very close to the origin, it turns out that the higher polynomial terms contribute less and less, right? Because x are getting smaller values. And if x approaches 0, then x squared is approaching 0 much faster than x. And x to the power of 3 is approaching 0 faster than x to the power of 2, and so on. That means if we are close enough to the origin, the only term that really contributes would be x itself. That means if we could argue that we are not looking at any point far away, like this in the phase diagram, but only at these points that are very, very close, like here, to the origin, where x is that small, that x squared and x to the power of 3 are already very close to 0, then we could ignore all these higher terms. And if we ignore all these higher terms that we have here, then we would get a very simple expression. That is, we would approximate the function f dependent on x and y just by two parts. That is, the linear growth in respect to x and the linear growth in respect to y. So with other words, we are plotting a vector field that are just straight vectors like this that do not have any curvature. They are just straight slopes. So we would assume the entire phase portrait would look like this. Straight lines approaching or repelling from the 0. Okay, so this is cool, because now instead of looking at the very complicated form of f and g, we can simply just use the linear parts as an approximation and reduce all the higher order terms based on the argument that if we are close enough, then x is small enough that x to the power of 2 or x to the power of 3 are actually 0. That means we are left with this. Well, that means the entire function is now described by 4 parameters. The parameter a, the parameter b, and the parameter d. And these parameters need to be determined from the original function. When we learned about Taylor series expansion, we learned that actually these parameters correspond to the slope of the function. That means we can approximate the function f of x by just saying it's a times x, and a is the slope of the real function in respect to x at the origin. So that gives us now an even analytical expression to compute the coefficients, these 4 coefficients that we need to approximate the behavior in the very close vicinity, close to the origin. So to summarize, we started with just rewriting f and g based on the Taylor expansion. We included all higher order terms. We then argued if we are close enough to the origin, then x to the power of 2 and higher polynomial orders will be 0, because they approach 0 much faster than x itself. The same, of course, holds for the parts in relation to y. So if we exclude all higher order terms, we have an equation that is simple, that just has essentially the ability to approach the origin on a straight line with different kind of slopes. And the slope is determined by the coefficients a, b, c, and d, which we know from Taylor expansion we can compute by just the derivative, the partial derivative of the function in respect to the variable that we are using. So A, for example, is a partial derivative of f in respect to x, and B is a partial derivative of f in respect to y. That means we are approximating, finally, the function f and g that is describing x dot and y dot with a very simple analytical expression saying a times x plus b times y, and y is c times x plus d times y. And a, b, c, and d are defined by the exact f and g that is given to you. So we can even interpret this now in a very nice fashion. Because once we actually describe this in such a way that we have this additive components x of x and y for the two changes of x dot and y dot, we can transform that into just a very simple matrix notation. And we do this by just making the hypothesis that we can write it this way, saying x dot is actually computed by a times x plus b times y, and c times x plus d times y. Well, seems to work, right? So we can use this matrix notation, multiplication with the vector, as a substitute of writing this set of two differential equations. So that means we have now a vector that is composed of the change in the x and the y direction that is equivalent to a matrix composed of the four partial derivatives a, b, c, and d multiplied with a vector of x and y. So with other words, if we think about a vector field again, then this just means that if we have a certain position x and y, let's say we're here, then the matrix L, which is very important and therefore it's called Jacobian matrix, tells us the orientation of the vector of the change, because the vector that is indicating the change is this vector here on the left hand side with an x component of the x change and a y component in the y change. So that means as an input this equation gets x and y, and as an output we get a vector at the position x and y that is telling us how the system is changing. So given this graphical interpretation, we can now interpret each of the four different variables a, b, c, and d geometrically. A describes how much the system is changing when the system moves in the x direction, right? B describes the change of x when y changes, and C describes the change of y when x changes, and D describes the change of y when y changes. So we decompose this in the four principal types of changes dependent on x and y. Well, this is great because we can now understand what is happening. But actually, it's actually not sufficient to really understand the principal behavior, because what we really were after were to describe whether the system is actually pulled back or pushed back to the origin, if it's actually subject to very small noise or starting somewhere in the vicinity, right? So we wanted to know whether, for example, if we start here, the system would actually push to the left-hand side, and if we start here, the system push to the right-hand side. If that is the case, then we know on this axis that the system would be an attractive direction, and the same on the y-axis as well. But how about this? If we would be here, an attractive condition would mean that the system has, if the fixed point is in the origin, has to approach the fixed point from the diagonal. That means we have to come up with two necessary conditions. If we are in the upper right quadrant, so if x and y are positive, then the change of both x dot and y dot needs to be smaller than 0. So instead of doing this like case-based analysis, where you study each of the different quadrants separately, you can also use a very elegant and also rather easy to apply mechanism. And that is actually the eigenvalue of a system. I know that many of you had trouble understanding eigenvalues and eigendirections. At the end of the day, this is actually not very difficult. So we start here with a matrix. This will be our Jacobian matrix in a second. So the basic idea is that if you do this operation with a matrix, you can imagine that you have a certain vector that you enter into the system. That would be the vector x and y. And it would be mapped on a new x dot and y dot. And for some vectors that we enter, we will get a vector as an output that actually points in the very same direction. So we have this as this. Second, I will highlight this. We have, for example, this here as an input, and we get a vector that looks, it's pointing in the very same direction. That is this one. The only difference is that this is longer or shorter. So if this happens, then we call the vector that has this property that it's mapped on the very same direction, we call it eigenvector. Eigenvector of the matrix, because depending on the matrix, this vector has to have different orientations. So that means the direction in which the vector has to point to be mapped on the very same direction again depends on the matrix itself. But the property that we are really looking at is not really the direction, it's actually the eigenvalue. Because the eigenvalue tells us whether this new vector that we get after the projection is longer or shorter than the original vector. If it's longer, then the eigenvalue is larger than 1. If it's smaller, then the eigenvalue is smaller than 1. And we will, which is actually presented here. So mathematically we say we have a matrix, in our case a 2 by 2 matrix, that is multiplied with a vector. And what we are getting is the very same vector. Then we call this eigenvector. But it's scaled by a factor of lambda. And lambda is telling us how much it's stretched or shrinked. So this decomposition into the eigendirection will allow us a really cool trick. Because if we want to determine the stability, we have seen on the last 10 slides that we would have to go to many different combinations of parameters. So that would mean we would have to determine the combination, the parameters, so 4 different parameters, A, B, C, and D, and then we would have to discuss the impact of these parameters in the different parts of the phase plane. What we are doing, however, is we will look into directions of principal changes. That means we will look for a vector field for which we are pointing in the very same direction. And then we will analyze only in this direction whether after the application of the matrix the vector is shorter or longer. And if it's shorter, then the point is going to the fixed point. And if it's longer, it will be repelled. So that means it's all in the information of the lambda that we are looking for. So here you can actually see that. So if we have an example, if we have such a situation that we have an x and a y axis, like here, and we have a vector field surrounding the origin, what we are doing is we're looking for the eigenvalue and the eigendirections of the local linear analysis at this very same point here. And we will find that there are principal directions in which we are repelled and principal directions in which we are attracted. If we do this and we do the local linear analysis, you will find that you have an eigenvector pointing along the y-axis. And in this direction, the eigenvalue is smaller than 0. That means in this direction, it's attracted. And in this direction, it's repelled. That's the second eigendirection. And the second eigendirection has an eigenvalue larger than 1. So that means we have one which is repelling and one which is attractive. And that means overall, the fixed point is repelling. It's an unstable fixed point. So it's essentially the trick is to look at the new basis that expresses the change in the two principal directions, which here coincide with the y and the x-axis. This does not have to be necessarily like that. A principal direction could also, for example, this principal direction, but here in this example, this is the principal direction which is along the x and the y-axis. Keep in mind, if we have an n-dimensional system, we should have n eigenvectors and n eigenvalues if the system has full rank, which usually is the case in our examples. Since we're interested in the eigenvalue primarily, we can compute it immediately. To this end, we use a characteristic equation. The characteristic equation is equivalent to the determinant of the Jacobian matrix minus lambda on the diagonal equal to 0. To remind you on the rules for computing the determinant, you multiply the elements on the diagonal and you subtract the elements on the off diagonal. So this gives us this characteristic expression that has to be 0. To solve this, we collect all the terms that are going as lambda squared, all the terms that are multiplied with lambda, and all the terms that do not include any lambda. We then identify that we can actually rewrite this in a simple fashion by substituting the coefficients, and we substitute the coefficient for the all the terms that only are linear with lambda and call this tau, which is a plus d, and all the parts that have no lambda we call delta, which is a times d minus b times c. These two parts are equivalent to the trace and the determinant of the Jacobian matrix. So if we want to solve this quadratic equation and look for the lambda values that actually equate to 0 in total, we know that we can use the PQ formula or this characteristic equation and solve this, and we know that actually this is only different with the sign for the two solutions. In solution number 1 it's positive, in solution number 2 it's negative. So it's tau plus the square root of tau squared minus 4 delta divided by 2. So in practice that means for you that once you have actually done the computed the derivatives and evaluated the derivatives at the point of the fixed point, you can actually compute immediately with the Jacobian the tau and the delta, plug it in and compute the value. Fine. Looks great, but what happens if actually the part that is under the square root that we have here, which is tau squared minus 4 delta, becomes negative? If it becomes negative, then we cannot actually easily compute the solution in terms of the square root, because the square root is firstly only described for positive values. In the next slide, we will show that this actually works if we extend the solution to complex numbers. And then the solution is either the two solutions that we will actually get are so-called complex conjugates, because the second part will be an imaginary part that we have here, and the first part is real, and that means that the solution finally is a real part that is identical for the two solutions, which is composed of tau divided by half plus an imaginary part that actually is different in signs. And these special solutions that are only different in sign for the imaginary part we call complex conjugate. A quick reminder of what that means. If we compute the square root of x squared, then the square root is the inverse function of x squared, right? Then y is a real number, because x squared is always positive. If, however, we compute the square root of minus x squared, then we are computing the square root of a negative number. We can express this as the square root of minus 1 times x squared, which we can factorize into the square root of minus 1 times the square root of x squared. And since we know that we cannot compute the square root of minus 1, we're introducing a new type of number which we call a complex number, and say that now the square root of minus 1 is just I. And this allows us to solve this equation, because now the square root of minus x squared is nothing else as I times the square root of x squared. And this we can compute. This sounds like a dirty trick to actually extend this, and you can actually see this if you want. You can actually see this as a trick to extend the square root operation to numbers that are negative. Even though that sounds unnatural for you, this is now a way to handle this mathematically. However, given the properties of the complex numbers, there are a lot of very useful mathematical features arising from that. So in general, we compose then a complex number of a real part, that is here x, and an imaginary part that is given by y. So that means a complex number has two parts, a real part and a complex part. In this way, then x and y themselves are actually an element of R, and we are rendering it complex by multiplying y with I. We can also define a property that is then called complex conjugate. So the complex conjugate of C, which we call C prime, is nothing else as the same real value but different sign for the imaginary part. So C and C prime are identical in respect to the real part, but have a different sign in the imaginary part. In that sense, if this second part here turns out to be negative, right? Because the square root turns out to be negative, then the second part would be element of an complex of the room of complex numbers. That then would mean that given we have the sign change here and here, the two solutions of lambda 1 and lambda 2 are so-called complex conjugates, which means the real part that is given by tau is the same, and the imaginary part is the same in size, but different in sign. So that means that the solutions, lambda 1 and lambda 2, are either both real or they are complex conjugate. A next short insight of what kind of consequence that had. For that, we would like to look at the differential equations again that we actually use to approximate the system. So once we did the local stability analysis, we assumed that the change of x can be just described in the local vicinity by a times x plus b times y, and the change of y can be given by c times x plus d times y. So we then express this as the Jacobian matrix A, B, C, and D, right? That means we can now rewrite again the change in terms of a matrix notation. So on the right hand side we have the Jacobian matrix times x vector, where x is a vector of x and y. And on the left hand side we have the change of the vector x and y in respect to t. If we have such a linear differential equation, a general way to solve that is to make a so-called Ansatz. So we make a guess. And the guess would be that we have exponential behavior. So we would guess that we have a speed with which the system is changing times e to the power of lambda t. So what we would have to do now is we would have to actually use this guess and substitute that in to our x that we have in our original definition. That's what we do. We compute the derivative of our guess in respect to t. So, well, since this is an exponential, the only effect that we will see after differentiating is that we will get the lambda in front of the equation. So that means this is the differentiated signal of our guess. So it's the solution of the differentiation. On the right hand side, we just plug in our guess. So we can try to solve this. So what we see is that we are getting lambda times a times e to the power of lambda t is the same as a times v times e to the power of lambda t. And if we do this, then we can actually isolate on both sides the e to the lambda of t, divide through it, and we get an equation that looks like this. We get a times v is lambda times v. So that means we assumed a certain solution, and we now got an equation that allows us to determine a to have this guess with its 4 parameters fulfilled. If we look closely, we realize immediately that this is again an eigenvalue problem, because on the left hand side we have a matrix. On the right hand side we have a scalar, and the vectors are identical. So what we are really looking at is we're looking for an eigenvalue problem that maps the value v onto the very same value v, and giving us a chance to determine lambda. So keep in mind again, if we have a matrix A that is n cross n, and we compute the eigenvalues and eigenvectors, then we have at most n eigenvalues and eigendirections, and at least one. So since we have more eigendirections, we have more solutions. If we look at our ansatz for the differential equation, for a solution of the differential equation, we realize that actually any of the different solutions, of the individual solutions, would be a solution to the system. And therefore also any additive solution that is composed of the individual parts would be a solution. So therefore, we make the second ansatz, and that is the solution of the system is a linear combination of all the different solutions with solutions in the different eigendirections and eigenvalues. So that then means that we can make this explicit, which is the solution of the system for a two-dimensional system is an exponential in the first principal direction with the corresponding first eigenvalue lambda 1, and in the second eigendirection with the corresponding second eigenvalue lambda 2. That we get like two principal type of behaviors. We either have, if both are real, behavior that looks like this. It's either exponentially increasing or it's exponentially decreasing and approaching a certain fixed point. If it's complex, we have the very same. It's either increasing or it's decreasing. However, this increase and this decrease is modulated with an additional periodic factor that can also be negative. That means if we look at this one here, then the solution is a damped oscillation that would look like this. The oscillatory part comes from the second half of the equation and the damping comes from the first part. Or it's an exponentially growing oscillation where the amplitude envelope is actually described by this prefactor. As a matter of fact, we can actually use this now to use only lambda 1 and lambda 2 to describe stability. With the very same reasoning as before, we can simply use also the idea from the last slide to characterize stability by just looking at lambda. So it's immediately unstable if one of the two eigenvalues is positive or has a positive real part, because then it's exploding. And if there is no such positive eigenvalue, then it's actually stable. So this then allows to actually make a very nice plot that actually uses the lambda, the tau, and the delta that we used when we compute the local stability analysis, which was corresponding to the determinant and the trace of the Jacobian matrix, as you can see here. And we're plotting now the different solutions in respect to changes of tau and delta. And we are separating the entire phase plane into tau smaller or larger than 0 and delta smaller or larger than 0. And if we do this, then we have regions for which we can compute the stability. We get this very nice boundaries here. And this very nice boundary that you can see here is separating the entire space in respect to the type of solution that you get, whether it's imaginary, whether it has an imaginary component, so whether it's real or complex. So with other words, the equation that we have here, that is just the stuff that we have below the square root. If that is actually smaller than 0, then we have a complex solution. a complex conjugate solution even. If z is larger than 0, then we have only real eigenvalues. So that means this green boundary tells us whether we have a solution that contains a complex part and therefore a periodic orbit or a periodic component. Everything inside this here has this periodic component. Everything outside of this area does not have this periodic component. So let's start with solutions that do not have a periodic component. So everything outside this green area can be further separated into a left side of this area, which is this one. In this area, we have one of the two directions being repelling and one of the two directions being attractive. The result of this is that we get a so-called saddle node that is attracting in this direction, for example, and repelling in this direction. Since it's repelling in one of the two directions, a saddle node is always unstable. So that means the orange left-hand side is containing all the unstable fixed point. The right-hand side, now, for the regions that are not green, contain the two alternative cases. The first one, that is the unstable fixed point, where you have real positive eigenvalues. Real positive eigenvalues mean that it's actually repelling in both principal directions for the two-dimensional system. And we have the yellow region that is attractive in both principal directions. And therefore, this is the only stable condition from the three. So we have the orange shaded region, which is unstable because one direction is repelling. We have the unshaded region, which I will shade now light blue, where we have one of the both of the two being repelling, and we have the yellow shaded region where both are attractive. And all these three solutions do not have a periodic component. Everything inside the green area has a periodic component. And we again have two different solutions. Above the center line, we have an unstable focus. That means we have an unstable solution, but instead of being repelled on a straight line, the system is repelled on the spiral, which corresponds to the periodic solution. And on the lower side, which is this red area, which I will mark now, we have a stable focus where the system is spiraling into the stable fixed point. So that essentially means if you want to determine the behavior of a two-dimensional fixed point, the only thing you have to do is you have to solve the eigenvalue problem, which we did on the last slide, and you characterize the type of solutions. You look first whether both are complex conjugate or real, and then you're looking at the positiveness or negativeness of your eigenvalues. So, for example, we have a node. We first determine the fixed point condition, which means both derivatives are 0. Then we compute the eigenvalues based on the local stability analysis. And we find that both eigenvalues are negative, smaller than 0. Then the node is stable. And if they are positive, it's unstable. If we have a saddle node, one of the two is attractive and one of the two is repelling, which means one of the two eigenvalues is positive and one of the two eigenvalues is negative. If you plot the topology of a saddle node in terms of a potential, as we did for a one-dimensional system many times, you see why it's actually called a saddle. This is actually the geometry of a saddle in 3D, and this corresponds to potential in as a function of the variable v1 and v2. And the system, of course, always tries to reach the lowest potential, so that means if the ball is initiated here, it will actually roll down the slope. If it's initiated here, it will roll this way. If it's initiated here, it will roll this way. If it's initiated here, it will roll this way, corresponding to the figure on the left-hand side with the force field. If you find that actually the square root is negative, you know that you have complex conjugate eigenvalues. And if you have complex conjugate eigenvalues, you immediately know that you're either spiraling in or spiraling out. And the stable focus then corresponds to a spiral that actually enters onto a fixed point and an unstable fixed point. It's a point that repels on a spiral to the outside.